those peaceful twinkling lights you see in the night sky? Well, they're not so peaceful. Every single one is a battlefield, a spectacular life or death struggle that rages for billions and billions of years. So let's dive into this cosmic drama. Because really, that's what a star's whole existence is. It's a constant, epic battle. You can think of it like a tightrope walk over a huge abyss, an incredibly fragile balance between two truly titanic forces. And when that balance finally breaks, the results are some of the most violent and, believe it or not, most creative events in the entire universe. So, what are these two forces locked in this cosmic tug of war? Let's meet the combatants. On one side, you've got the star's engine, and on the other, an unstoppable, relentless foe. In one corner, you have nuclear fusion. The star's core is just this colossal furnace smashing atoms together and generating a phenomenal outward pressure. It's literally trying to blow the star apart. And in the other corner, gravity. It never gets tired, it never stops, and all it wants to do is crush every single particle of that star down into the tiniest possible point. For billions of years, these two are locked in a perfect stalemate. But here's the thing. There's a catch. That fusion furnace, it needs fuel. And that fuel isn't infinite. So when the tank finally runs dry, fusion just stops. The outward push is gone. And suddenly, after billions of years of perfect balance, the whole thing is broken. Gravity, which has been patiently waiting this whole time, finally gets its shot. So what happens when gravity takes over? Does the star just fizzle out, or does it go out in a blaze of glory? Well, its entire destiny, its final fate, it all comes down to just one thing: the mass of the core it leaves behind. You see, depending on how much stuff is left over, a star can go down one of three paths. The lightest cores, they get to retire gracefully as a white dwarf. The middle rates, they go through a cataclysmic explosion and leave behind an ultra-dense neutron star. But for the true heavyweights of the universe, their fate is gravity's ultimate victory, a black hole. So where's the dividing line? The first crucial threshold is this number right here, 1.44 times the mass of our own sun. This is the famous Chandrasekhar limit, named for the physicist who figured out that this is the absolute maximum mass a star's core can have and still be held up by a very specific quantum force. And this is where we enter the really bizarre world of quantum mechanics. As gravity's crushing the core, the electrons inside start to fight back. There's this rule called the exclusion principle, which basically says they refuse to be squeezed into the same space. It's like a quantum social distancing rule. This resistance creates a whole new kind of outward pressure. It's called electron degeneracy pressure, and it's just strong enough to stop the collapse, creating a stable, Earth-sized ember we call a white dwarf. But that quantum defense, it has a breaking point. So what happens when a stellar core is heavier than that 1.44 solar mass limit? What happens when it's so massive that not even quantum physics can save it? Well, the collapse keeps going, and things get intense. The pressure becomes so overwhelming that it literally forces electrons and protons to merge together, creating a sphere made almost entirely of neutrons. This is a neutron star, and its density is it's mind-bending. A single teaspoon of stuff from a neutron star would weigh billions of tons here on Earth. That's more than all of humanity combined, concentrated into something you could hold in your hand. But even the incredible strength of a neutron star has its limits. If the collapsing core is more than about 2.5 times the mass of our sun, no known force in the universe can stop the crush. Gravity wins, period. And we've finally arrived at the point of no return. This is where things get truly strange. The collapse becomes unstoppable. It creates an object with a gravitational pull so immense that nothing, not even light, can escape. But how is that even possible? How does gravity get so strong that it can trap the fastest thing in the entire universe? Well, this is a great way to picture what's happening. As the star collapses, its gravity gets stronger and starts to bend light back on itself. The possible escape paths for a beam of light, this escape cone, it just gets narrower and narrower until at one critical point it snaps completely shut. Now every single path leads inward. That's it. That's the event horizon. And just like that, a black hole is born. The star's core has collapsed down to a point of infinite density. It's the moment the cosmic tug-of-war finally ends. Gravity has won the battle, absolutely and finally. So this all sounds pretty grim, right? Collapse, destruction, points of no return. But here is the most beautiful and profound twist in this whole story. The death of a massive star is also one of the most important acts of creation in the entire cosmos. It's a fantastic paradox when you think about it. The supernovae that announce the death of these stars are the most violent explosions you can possibly imagine. And yet, at the very same time, they are the universe's greatest forges. They're its grandest acts of creation. Because it's inside the unimaginable heat and pressure of these explosions that all the heavier elements get made. We're talking about the building blocks of planets and even life: carbon, oxygen, iron, even the gold and platinum in our jewelry, the uranium that powers our reactors. All of it was forged in the final dying moments of a massive star and then just scattered across the galaxy. And this just brilliantly illustrates one of the most poetic truths in all of science. The carbon in your DNA, the oxygen you're breathing right now, the iron in your blood, every single one of those atoms was cooked up in the heart of a star that lived and died long before our Earth even existed. We are, quite literally, the children of the stars. We are made of star stuff. So we've journeyed from a star's life to its death, and we've seen how that death actually gives rise to new life. But the story isn't over. Not by a long shot. Black holes, gravity's ultimate victory, remain one of the deepest mysteries in all of science, and our understanding is changing all the time. I mean, just look at what the James Webb Space Telescope is finding right now. It's peering back to the dawn of time and spotting these mysterious little red dots. Scientists think these could be some of the very first galaxies, powered by supermassive black holes that grew way bigger, way faster than any of our theories thought was possible. And that's a huge puzzle. We just don't have a good explanation for how they got so big, so early. It's a discovery that's challenging everything we thought we knew. Which leaves us with a final, really tantalizing question. We know the death of a star creates the stuff for new beginnings. But a black hole? Well, it seems like a true end. So what happens to the information about all the things it swallows? Does it just vanish from the universe forever, breaking the known laws of physics? Or is it somehow preserved in a way we just can't understand? Yet. Now that's a mystery for the next generation to figure out.